when you're doing these chemistry problems, make sure that you have your reference guide out. Even if you don't know so many topics, these things can just help you really easily, So I just wanted to say that. According to the wave mechanical model, an orbital is defined as the most probable location of what? Well, these types of questions, if you don't know them, you don't know them. If you know them, you know them. The wave mechanical model is, the answer for this one is an electron. Basically, right, normally you see models of the atom looking somewhat like this. So let's just say this is the nucleus of your atom with your protons, with, let's say, your protons and your neutrons, right? And then on the outside, you got outer kind of shells that you have, right? You might see atoms drawn like this. But actually, the most accurate representation of an atom is actually something called the wave mechanical model, or the quantum model of the atom. And it was developed by a dude named Erwin Schrödinger. Basically, it shows kind of the probability of an electron at a certain area. So all of these dots represent kind of possible locations of an electron. So electron can be here, it can be here, it can be here. But notice how as I get further away from the atom, the chances of an electron being there are less and less. And that kind of makes sense because electrons are negatively charged and they're attracted to the positively charged nucleus. So they want to be as close to it as possible. When they start kind of heading out like this, they're at like an unstable kind of state. So the likelihood of them being out here is going to be far less than, if they were closer to the nucleus. And another important thing about the wave mechanical model is that if you know it's the principle of uncertainty. Basically, it's basically like if you know the closer you know to where an electron is. So let's say if I start narrowing down on the position of electron, well, the less information I get about the speed. So the more I know about an electron's location, the less information I know about its speed. But the more information I know about the speed of the electron, so if I know an electron is traveling like, let's say, this fast, well, the less I know about the electron's position. So it's kind of like you either have one or the other. It's kind of weird. The part of the atom that has, okay, you're cooked if you don't know this one. But even if you don't know this one, right, at least know that when you have an atom, the inside part or the center of the atom, you got the nucleus, right? Okay, let's go to our reference side. Inside the nucleus, there are protons. And protons are positive, right? Protons are positive. You can see here, okay. So right over here, this is our reference side, this is the table O, and neutrons have no charge, right? This is why they're called neutrons, because they're neutral. So they have 1 AMU, so this is their weight. This one up top represents their weight. So they have 1 AMU, and they have 0 charge, so 0 charge. Right? A proton, it also has a weight of 1 AMU, but this time it has hydrogen atoms. I want to highlight the P. Both of them represent protons, so I want to highlight P. So this right over here can represent a proton, or this one, or like a hydrogen nucleus, but this right over here represents a proton, and this one up top, well, that represents the weight of the proton, it's 1 AMU. However, at the bottom here, this one right over here represents that it has a charge of +1, right? So this is what this one represents, as a charge of +1, right? For example, if I were to look at an electron, a beta particle, basically it's a fast-moving electron, but right over here, notice how an electron has a weight of 0 AMUs. It barely weighs anything compared to a neutron and a proton, and the weight's basically 0, and it has a charge of -1. It has a charge of -1. Anyways, I don't know why I'm spending so long on like such an easy problem, but okay. So overall positive charge, that's going to be the nucleus. Oh, which subatomic particles each have a mass of approximately 1 U? We just said, right? 1 U is the same as 1 AMU, just so y'all know. So basically, we just said that a neutron, 1 AMU or 1 U, proton, 1 AMU or, 1 AMU, right? So neutron and proton should be our answer. Yep. All right, this one's another one where if you don't know it, you don't know it. The discovery of electron was by a dude named J.J. Thomson. I think this is how you spell it. It's Thomson without a P. I think that's how it's spelled. It's a really weird name. But anyways, he basically did a cathode ray tube experiment where, let's just say this is the ray tube. And what he did was he shot electrons. He basically shot electrons out of the ray tube. He didn't know it was electrons, but, what was happening was he shot electrons out. And basically, let's just say he put a positive charge here, right? Let's say there was like a positive charge here. And let's just say there's a negative charge here. The electrons are negatively charged, right? So they're going to get attracted to the positively charged area. So, this is kind of how he found out that in the atom, there was kind of another type of particle in the atom that has a negative charge. Obviously, I'm oversimplifying this. He also used like magnets as well, because charge is like a moving charge in a magnetic field. And what that's going to do is that's also going to shift the particle in some direction like this. So, he also did that. Basically, he discovered the electron. So, yeah. And this was called the cathode ray tube experiment. So, yeah, cathode ray tube. Elements on the periodic table are ordered in what? Well, let's go to the periodic table. Where is it? Periodic table should be somewhere here. And this is, I don't know what table it is, but you should see it. And basically, look at this. So we have element 1, element 2, element 3, element 4, and so on, right? And all these elements are ordered in increasing. All of them are ordered in increasing. All right, so their order is in kind of increasing number of protons. So for example, element 1, hydrogen, has 1 proton. Element 2, helium, has 2 protons. Element 3, lithium, has 3 protons. So these bolded numbers right over here represent the amount of protons they have. And notice how in the periodic table, they're ordered in increasing amounts of protons. Which element is classified as a metalloid? So if you go to their periodic table, notice how there's like a little ladder or stair, whatever. And guess what? If you draw a ladder back up, I don't know why I call it a ladder. If you draw stairs back up, all of these elements right over here are semi-metals or metalloids. They're basically half metal. So they have some properties of a metal and they have some properties of non-metals. So which element is classified as a metalloid? Well, the first one that stands out to me is Te, because what I notice about it is if I go back to my stair diagram, Te is highlighted right over here. So I can just highlight Te as my answer. STP, O2 and O3 are 2 forms of the same element that have what? We need to know about these 2 things. They're allotropes of each other. They are allotropes. Meaning that, all right, both of them are made out of the same element. They're both made out of oxygen. However, they have different structures. All right. So O2 looks something like this, and they have 2 lone pairs. I'm too lazy to draw it. But you also have O3, which is basically something like this. This is O3. And they have the different molecular structures, obviously, right? Because different amount of atoms, right? You can kind of suspect that they have different structures. So therefore, they're going to have different properties. So we have different molecular structures, but they have different, and that leads to different properties between the atoms. One atom gives you life, which is oxygen, right? Oxygen gas, and one gas is really bad for you if you get exposed to it, and that's ozone. Which substance cannot be broken down by chemical means? So any substance that cannot be broken down by chemical means, that's an element. Elements cannot be broken down any further. All right, elements cannot be broken down any further. Water, right? Water, because it has 2 different elements, you can break this down, right? You can break this down into hydrogen. You can break this down into oxygen via electrolysis. If you're doing that, right? You can break down into the individual elements. But elements itself, let's say if you wanted to break down, let's say, I don't know, just silicon, for example. Silicon is right over here. Let's say you want to break down silicon. Well, you can't really, because it's just the element by itself. It's not really bonded to anything else. So, which one of these is an element? You have aluminum, and you have argon, and you have antimony. Antimony is, let me see. All right, but you see, antimony is right over here. Let me just flip this. My bad. But notice how antimony is element 51, right? It's element 51. And notice how all of these answer choices are elements. We said how elements can't be broken down any further, but we have to be careful. We have to read the question, right? We want to find what substance can be broken down by chemical means. So if elements can't be broken down by any chemical means, then what substance can be broken down by chemical means? AKA what substance has more than 2 elements, right? 2 or more elements in it, right? And in this case, it's ammonia. Ammonia is NH3. It has, right, nitrogen, and it has hydrogen. Therefore, by some process, the Haber process, I can break this down into nitrogen and hydrogen. But you don't even need to know that. You just know that, okay, I see 2 different elements. Well, I can break these down into their individual components, right? Meanwhile, all 3 of these answers are elements, they can't be broken down any further, so I'm just going to cross them out. All right. Which statement describes, all right, these two? If I look at all these answer choices right over here, all right, both of them are compounds. Both of them compounds, both of them are mixtures, same, different color. Okay, I've read the answer choices. First thing you got to know is, what a compound is and what is a mixture. A mixture is pretty straightforward. Mixture, all right, let's talk about compounds first, actually, because this might make more sense if I talk about it like this. So, compounds are just when you have, so you got 2 or more elements in a compound. So, for example, let's say if I have water. Water, for example, is a compound because it has 2 or more elements. 2 or more elements, okay? So it can have 2 or more elements. Mixture is just when you combine 2 compounds together physically. 2 compounds together. 2 compounds together. So for example, if I combine water and I combine table salt, right, I'm combining 2 compounds together. Therefore, this is a mixture. However, it's important to note that mixtures are just when you physically mix 2 things together. So if I mix water and salt together, I'm physically mixing them together. That's going to be a mixture. Mixtures are when they're physically mixed together. All right. Now, if you only have just plain regular water, H2O, this wouldn't be a mixture because there's only 1 compound. And for mixtures to be a mixture, you need 2 or more compounds physically combined together. All right. So that's something important to know. Now, notice how both of these things are compounds, right? Because they're only one thing, right? They're only one molecule in this case, right? If it was to be a mixture, then kind of you would need another compound in order for it to be a mixture. But both of them are only talking about, the question's only talking about one compound in this case, right? This compound, which isn't a mixture, it's a compound, and this compound, which isn't a mixture, right? Because it's by itself. So they are both compounds, and because of the O2 at the end, they're going to have different properties. All right, that's something important to know. Which 2 terms represent major categories of compound? So you have a couple kind of terms you have to know. So you have ionic compounds, you have covalent, and the covalent compound, or you can also think about this as the molecular compound. Right? An ionic compound is when you have a metal and then you have a non-metal, and they're bonded together. They are bonded together, and if a question occurs that talks about ionic compounds, I will go more in depth, but that's basically what an ionic compound is. Molecular compound is when you have 2 atoms. Let me just draw this. You have 2 atoms, and they both want a covalent shell, aka they want 8 electrons in the outermost shell. So right over here, notice how oxygen only has 6 electrons in the outermost shell, right? And so is the other oxygen. So what they do is they share these electrons, meaning that now in this case, oxygen has 1, 2, 3, 4, 5, 6, right? Because this oxygen shared one of its electrons here, and then 7, 8, because this oxygen shared another one of its electrons here, right? Remember, imagine if this oxygen shared 2 of its atoms here. So now this oxygen is feeling happy because it has 8 electrons. And this oxygen right over here shares both of its electrons to this oxygen atom. So they both share their electrons. So now the second oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. And both of these atoms have 8 electrons. Their sharing of electrons are denoted by kind of a mark right over here. And, well, that is kind of the main idea behind a covalent compound or a molecular compound. Nuclear compound, that would be pretty crazy, I'm not going to lie. Empirical and molecular compound. Let's just kind of review these answer choices. The empirical formula, this is how you say it. So the empirical formula basically shows you the ratio of the atoms in a molecule in the simplest form. So notice how this H2O4 can be represented as HO2, right? If I kind of simplify everything, if I kind of divide, I mean, this is pretty cursed, but imagine if we divide the amount of atoms in both of the atoms. I mean, imagine if you divide this molecule from by 2, basically. So you get HO2, right? 2 divided by 2 gives you 1. 4 divided by 2 gives you 2, right? And now it's kind of in its simplest form. But this isn't like the major category, right? This kind of just represents kind of like a simplifying way, I guess, to represent a molecule, but it's not really like a major category of compounds, right? Just the way to kind of simplify compounds, but it's not actually like, a category of it. So the empiricals we can get rid of. Nuclear, I don't even know what that is. So yeah. Which formula represents an asymmetric molecule? What do I do here? Well, let's take a look at CH4. Let's take a look at CH4. What do you think CH4 looks like? So right over here, I have CH4, I have N2, and I have CO2. N2, CO2, and H3. Asymmetric, okay. Formula represents an asymmetric molecule. So how do I do this? Well, I'm going to draw out all of these atoms. So carbon likes to have 4 bonds. And luckily for us, we have 4 hydrogens. So what we're going to do is we're going to draw 4 hydrogens. Right? Carbon likes to have 4 bonds. Check. Hydrogen likes to have 1 bond. So this hydrogen likes to have 1 bond. This hydrogen likes to have 1 bond. Check. And a good rule of thumb is something called the honk 1, 2, 3, 4 rule. Hydrogen likes to have 1 bond. Oxygen likes to have 2 bonds. Nitrogen 3, carbon 4. Really good rule. So in this case, CH4, obviously symmetrical. Generally, when molecules are symmetrical, they're nonpolar. They are nonpolar. So, in order to explain this, I need to go through quite a lot of stuff. But basically, where the hell is my thing? Okay. So, in all of these atoms right over here, they have something known as an electronegativity value. Basically, how much does that atom want to attract an electron, right? So, for example, if I have something like water looks something like this. All right. Oxygen, it turns out that oxygen has an electronegativity value. Hopefully y'all can see that. But oxygen has an electronegativity value of 3.4. The higher the value, the more attracted they are to kind of the electrons. So oxygen has an electronegativity value of 3.4. Hydrogen, electronegativity of 2.2. And notice how in a water molecule, this is actually a covalent compound, right? We said how these little marks represented 2 atoms sharing electrons, right? So oxygen really likes these electrons, right? So what's going to do is it's going to kind of hog quote unquote hog the electrons. It's going to kind of bring the electrons closer to the oxygen. So electrons they're going to be a little closer to oxygen than they are to hydrogen. Most of the time, they're going to be a little bit closer, right? Because oxygen really wants these electrons. I mean, there's like a lot of ranges for this, but I'd say that when the difference between the electronegativity value, so basically, if you take these values and you subtract them. Now, if you take these 2 electronegativity values and you subtract them by each other, and in this case we get 1.2, right? And if the answer is in between 0.4 and 2, this represents a polar molecule. And basically, oxygen, because it really likes these electrons, and it kind of brings the electrons closer to oxygen, it's going to have a partial negative charge. So it's going to have sort of a partial negative charge, which is kind of this S-shaped thing, and then a minus sign. Hydrogen, they're kind of getting their electrons taken away by oxygen. And if you have a negative charge taken away, you're going to be more positive, right? You're going to have a partial positive charge, right? Hydrogen, originally neutral, right? Hydrogen had the same number of electrons as protons. But if the electrons are kind of slightly tilted towards kind of oxygen's kind of attractiveness to electrons, well, they're kind of getting, it's kind of like their negative charge is getting stolen. So they're going to be partially positive, but not fully positive because they're still sharing the electrons, but it's more in oxygen's favor. So that's kind of the thing. And for a molecule to be nonpolar, well, it's just going to be whatever electronegativity value you have. So the difference in your electronegativity has to be less than 0.4. But the value should still be greater or equal to 0. You can't have a negative electronegativity value. N2. If I have 2 nitrogen two nitrogen atoms. All right. Now, how many electrons, how many valence electrons does nitrogen have? So nitrogen is in group. You can think about this as this right over here is group 1A, right? This whole row. This whole column right over here. This is a row. This is a column. Keep getting myself confused with this. All right, but this column right over here is 1A. This column is 2A. This column is 3A, 4A, 5A, 6A, 7A, 8A. It turns out that nitrogen is in group 5A, and it turns out that every atom here has 5 valence electrons. In this case, right, I mean, if you have an atom, right, let's say this is nucleus, and let's just simplify things and say that these are our shells where electrons can kind of reside in. The electrons that are in the outermost shell are called the valence electrons. And it turns out that because nitrogen is in group 5A, it's going to have 5 valence electrons. And so is everything else in group 5A. If you're in group 1A, you're going to have 1 valence electron. Group 2A, 2 valence electrons, and so on. So the periodic table is quite amazing because even though it might just seem like, okay, it's an increasing kind of atomic number, so what? So the periodic table is quite amazing because even though it looks like, okay, it's an increasing atomic number, right? But, in reality, there's actually kind of a lot of hidden patterns that you don't see. So in this case, nitrogen has 5 valence electrons. So I'm going to draw them. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These dots represent our valence electrons. Now, let's share electrons because we have to get a full valence shell. Remember, atoms want a full valence shell. So our goal is to have 8 electrons on the outside. Okay. So 1 bond, 2 bond, and let's create a 3rd bond because we said that nitrogen likes to have 3 bonds. So each bond effectively counts as 2 electrons. Each bond counts as 2 electrons. Because think about it, you have 1 electron from your side and 1 electron from the other nitrogen. So effectively, 1 bond counts as 2 electrons. So let's look at this nitrogen atom. You have 2 from here, plus 2, which is 4, plus 2, which is 6, 7, 8. Check. This nitrogen is happy. Let's take a look at the other nitrogen atom. 1, 2, each bond counts as 2. So there's 3 bonds, meaning that there's 6 electrons from all of the bonds in total, plus these 2 is going to be 8 as well. Check. This nitrogen is also happy, and it's symmetrical, right? And that means that it can't be our answer. It's symmetrical. Okay. And it's also nonpolar. Keep that in mind as well. Now, NH3. How do you think? So nitrogen likes to form 3 bonds. Right, from the honk 1, 2, 3 rule. Now, some of y'all might think that NH3 looks like this, where the angle between one hydrogen to the next hydrogen, they're all the same, 120 degrees. However, this isn't actually the case, and the reason why is because, right, we saw how in this example right over here, when nitrogen creates 3 bonds, it's gonna have two electrons remaining, right? Or 1 lone pair remaining, right? That's not bonded to anything. It's going to have 2 electrons remaining. So let's say if I draw 2 electrons. Well, the thing about these electrons is that they're going to actually kind of repel the hydrogen atoms. So this isn't actually the way you draw an NH3 molecule, because these electrons, I mean, for this structure, these electrons are placed in a way where, the electrons are just going to kind of repel the electrons from the hydrogen atom, and this isn't really going to be the most accurate representation of the ammonia atom. So the atom looks something like this. And then you have your 2 electrons up here. All right. And notice how the electrons are sort of away. They're further away from the hydrogen atoms, right? Because the hydrogen atom electrons, right? They repel each other, right? Same charges, like charges, repel each other. So if we have this electron up here, and down here, then they're going to be repelled to each other, right? They want to be as far away from each other as possible. If we took this model, electrons are pretty close to every one of them. But in this case, right, the electrons are only somewhat close to these hydrogen atoms, but they're kind of like the furthest away from it. And this is not symmetrical. All right, this is actually asymmetrical. All right, this is asymmetrical. Look at all the other examples, right? We have N3 here, CH4 here, CO2 looks something like this. Right? They're all symmetrical. But then you look at NH3, and that's asymmetrical. And in addition, it's polar. So asymmetrical, you should have like a suspicion that it's polar. Symmetrical, nonpolar. All right. So we are going to pick ammonia, which describes energy changes formed, bonds are broken, and formed during a chemical reaction. Okay. So what happens during a chemical reaction? So let's say if I have, let's just give like a quick example. So during a chemical reaction, so hold on. Let me just do a quick drawing. So what happens during a chemical reaction is that bonds are being broken. So some bond is being broken, and new bonds are forming between the atoms or the molecules. So imagine if a lot of chemical reactions, they have to be heated. For example, like if you get a lighter, you have like a match, you have like a matchstick, and you rub it against like the match thing you're supposed to rub it against. It creates fire, and that right over there is a chemical reaction. So what's happening is this heat right over here, this molecule right over here is absorbing heat. It's absorbing energy, and as a result, the bonds are being broken. So as bonds absorb energy or heat, they're being broken, right? And when new bonds are forming, well, the opposite happens. They're releasing heat. They are releasing heat. All right. So that's something important to know. So which statement describes, well, let me see. Energy absorbs, bond broken, right? Energy is released when bonds are formed. Exactly what I just said. Oh yeah. A solid electrical current. Which type of chemical bonds are in the sample? Well, if I have just copper, so this is a biggest giveaway. A solid sample of copper. If you just have a metal atom, you have metallic bonds. You have metallic bonds. All right, I'm just gonna highlight the answer. It's talking about a solid sample of copper. If you just have a metal atom, it's gonna have metallic bonds. All right, that is the biggest giveaway that you should notice right away. What are metallic bonds? Well, think about it. You have tons of metals. Let's just say these atoms are metal atoms. What happens is they have something known as delocalized electrons. So they have electrons that are free to move around. They move around everywhere. Sometimes this is even known as a sea of electrons. These electrons move around everywhere. Now, this is actually why metals can conduct electricity, because they have a charge and it's moving. It's moving. So when you have a charge, in this case, my charge is my electron, right, which is negatively charged, and it's moving, well, that conducts electricity. So that's why metals are good conductors of electricity. Which 3 forms of energy? What are 3 forms of energy? Well, you can have thermal energy. All right, thermal energy in an object, you can kind of think about it. Let's say if we have like a hot cup of hot chocolate, all right, that's going to have thermal energy, right? Now, some people might be like, okay, but what about temperature, right? Temperature has energy. No, temperature is just a measure of how hot or cold something is. But thermal energy is kind of the more accurate way kind of to describe the energy from a given temperature. So if something has a really high temperature, they're going to have a high thermal energy. That's kind of the way you say it. But temperature just measures how hot or cold something is. All right, it's not actually, thermal energy is like the correct way to describe it. All right, you can have chemical energy, right? So if you have 2 atoms, right, once again, covalent bond, the energy is stored in this bond right over here, right? The energy is stored in this bond, chemical energy. And then you have electromagnetic energy, which you can think about as kind of light, right? You have things like X-rays. You have things like gamma rays, microwaves, right? Gamma rays, microwaves. All of these are forms of light, and they give off energy. Think about like an X-ray scan. All right, when you're thinking about electromagnetic radiation, one example that maybe should pop up to your head, you got gamma rays and you got X-rays. All right, based on table S, an atom of which, based on table S. So let's go to table S first. As soon as I see based on table whatever, I'm just going to go to that table. Based on table S, an atom of which element has the strongest attraction for electrons in a chemical bond? Oh, we just said the strongest attraction for electrons. Remember the kind of how much does an atom want to attract another atom, right? How much does atom want to attract, the electrons in another atom, right? Remember we said that's electronegativity. We said that's electronegativity, right? So in this case, let's look at chlorine's electronegativity. Chlorine has electronegativity of 3.2. Oxygen has an electronegativity. We said oxygen has electronegativity of 3.4. Nitrogen has electronegativity of 3.0. And selenium, it's good that these people put the names there. 3.6. Oxygen is our winner. Higher value equals higher electronegativity. The easier way to do this is a good thing to memorize is that electronegativity increases this way. So let me do this in a different color. Electronegativity increases as you go up this way. All right. And fluorine actually has the highest electronegativity. All the noble gases here. So all these elements right over here, because they have a full valence shell. So neon, for example, right? Neon has 8 outer electrons. And remember how we said atoms are happy, right? Atoms want a full valence shell. Well, it turns out that neon already has that full valence shell. It doesn't want any more electrons, so it has 0 attraction. It has 0 electronegativity. And so is the same for all of these atoms right over here. So the reason why electronegativity increases as you go up a group is because as you go up the group, the atom gets smaller and smaller. So imagine if the atom gets smaller and smaller, right? The electrons are going to be closer. The electrons are going to be closer to the nucleus. So because the nucleus is very close to electrons, well, if you have like another electron from another atom, well, it's closer to the nucleus, right? So it's gonna have a higher electronegativity because just the nucleus itself is closer to that electron, so it's gonna attract it more, right? And the reason why electronegativity increases as you go from, in this case, this represents a period in the periodic table. A period is just when you go from left to right in the periodic table. So the reason why electronegativity increases as you go from left to right in the periodic table is because, well, it turns out that the simple explanation for this is, well, you have more protons, right? You have more protons. And what's going to happen is the increase in the amount of protons is going to make it so that the atom attracts the electrons better. All right. Imagine how much easier it is to attract an atom with, let's say, 9 protons. Imagine how much easier it is to attract an electron with 9 protons compared to attracting an electron with 3 protons, right? 9 protons is just going to be way stronger. It has a way stronger positive charge, right? So that's the thing. You might be saying, okay, why does electronegativity increase up a group? Let's say sodium has 11 protons, right? And lithium only has 3 protons. Yet lithium actually has a higher electronegativity than sodium. And the reason why sodium actually has less electronegativity than lithium, and so is the case for all of them, all of these atoms right over here have less electronegativity than lithium. And the reason for this is because, well, you might need to know a little bit of physics for this, but basically it turns out that the distance right over here, so the distance from the proton to the electron, actually has more of an impact on a charge than the amount of protons. So imagine if we have a sodium atom, 11 protons, and a lithium atom with 3 protons, right? It just turns out that even though the lithium atom has less protons than the sodium atom, because the sodium atom is just so much further away, the nucleus is so much further away from the electron, it's just not going to attract it as much. It's not going to have as high of electronegativity as lithium. Think about like 2 magnets, right? If you have 2 magnets that are really far away from each other, even if they're pretty big magnets, they're not going to really attract each other that much. If you have 2 smaller magnets, but they're really close to each other, they're going to attract each other a lot. All right. And I'm not going to get into like the physics of it, but just know that there's priority over the charge. But just know that kind of distance has a huge kind of weakening effect between 2 charges. All right. Temperature, helium most behave like an ideal gas. What do you think is the answer to this? Well, what the hell is an ideal gas in the first place? And to answer this, the ideal gas follows the kinetic molecular theory. And this is basically assumptions on how a gas should behave. So, I'm kind of too lazy to write them out, but basically, one is that they have no intermolecular forces. So the main ones kind of you should know is that, you should know all of them, but they have no intermolecular forces. Their collisions are perfectly elastic, meaning that if, let's say, they hit the wall, they're going to bounce back with the same amount of kind of energy, right? They're going to keep their energy when they're doing their collisions. They're gonna, let me see. They're going to, bro, I'm not having a brain fart right now. They're gonna only go in straight lines. unless they hit a wall or they. And finally, the gas particle, the volume of the gas particle is so small that it's basically zero. All right, so the gas particle's volume is so small, it's basically zero. Okay. Now, imagine a scenario like this. So let's say you have a container and you have some gas particles. Now, obviously, the kinetic molecular theory, right? I mean, it's a theory, right? But it's not actually like reality. In reality, molecules are constantly, there is intermolecular forces, right? The kinetic molecular theory says there's no intermolecular forces between gas particles. Well, the reality is that there is intermolecular forces between molecules, right? So, ideally, gas particles have no intermolecular forces, but the reality is that they do. So, what actually happens is that things behave like a real gas. All right? And a real gas, basically, it does have attractions, and it does the opposite of what the kinetic molecular theory said. Now, if I wanted a real gas to behave like an ideal gas, I actually have to place it under low pressure and high temperature. Here's the reason why. Low pressure means that the container is pretty big. All right, so the container is pretty big, right? Because pressure is basically forced by these gas particles hitting the wall. So if the container is really big, they're going to hit the wall less often, resulting in less pressure. And high temperature. And what high temperature does is it makes the molecules or the gas particles move faster. So imagine if these molecules are moving really fast. Well, they're not going to be able to have the chance to attract each other. Imagine moving so fast that, you can't really attract the other gas particles, right? So therefore, the intermolecular forces between these atoms or gas particles is going to be basically negligible. And in addition, if we have a really big container, well, what happens is the volume of the gas particle compared to the volume of the container is going to be zero, right? And in addition, if we have low pressure, so if the container is really big, the gas particles are barely going to interact with each other, meaning that there's going to be less intermolecular forces. So, yeah, there's kind of a lot of reasons how under low pressure and high temperature, a real gas actually behaves a lot like an ideal gas. So in this case, this kPa represents pressure, or it's a unit for pressure. And K is Kelvin, it represents temperature. And we want to find out, we want low pressure and high temperature. So low pressure, high temperature.